the agenda, what we're going to cover. And after a brief intro, we're going to discuss kind of the problem space and with client identity and especially within the context of decoupled applications. We'll look at how DANE sort of maps to the problem space and helps to take some of the complexity out of it. And then I've also got some links for further reading. And then I'm going to ask you very nicely if you're interested to get involved with the effort at IETF. So let's jump right in. A little about me. I've been in the industry for a little over 20 years. Started out in support type roles, went through engineering and some security research here and there. And I'm currently technical director at Valimail in the sort of future technology group. Valimail started in 2015. The mission was to authenticate the world's communication. And we started with email because email's kind of, was on fire, and we think we've made some progress there. And now we're expanding into IoT and beyond, using some of the same sort of philosophies and patterns that work well for email and playing those back against application footprints that seem to be getting more and more complex and pushing some of the security boundaries. So the problems we're going to be talking about, mainly center around PKI-based identity. Most folks will agree that from a functional standpoint, PKI-based identity is a good thing to use. You get a lot of features from that you can't get from shared secrets. But the challenge is one of the biggest challenges in bootstrapping, right? And so that's not just, creating and protecting that private key, but in getting that attached to a public key infrastructure, and automating that can be brittle sometimes. It's either brittle or expensive. And given that it's usually an organization scoped PKI, getting that to work well across organizations has its own challenges, because you have a risk of naming collision and impersonation the more private public key infrastructures you have participating in the same application. And when you start to look at decoupled applications using message queues and brokers, if you don't have a public-private key pair used for generating and validating message signatures, then you really can't achieve sender non-repudiation. That's the only way to do it without having a shared secret. And middleware breaches do happen, and they can go undetected for years. If you've been watching the news, then there was something interesting happened recently. There was a middleware vendor who revealed that they had been compromised for like some 5 years. And so this is in recent news. This stuff does happen. And so be careful how much, not just, how much you trust your middleware, but what you trust it for. It's okay to trust it to be available and to deliver messages, but trusting it to enforce confidentiality and to enforce the integrity of what's going across it. You have to be careful with that, because it's a compromised middleware component is a great avenue for impersonation. You can impersonate anything that's expected to communicate across it if the messages themselves don't have some sort of identity verification strategy. And the foundational issues, that a lot of this stems from is, so if you consider that an identity is composed of an identifier, which is a name, a credential, which could be a password, it could be a shared secret of some sort, it could be a public-private key pair, just however you prove that you are the rightful holder of that identity, and then various metadata associated with it. When you create a private PKI or a CA, you essentially create a new namespace, right? And it enforces its own namespace within itself. But if you have multiple PKI, then you can have the same names having certificates issued across all of these PKI. They don't have a way of keeping others out of their namespace. And so the reason that this works pretty well for the web is because we have DNS and the CA bundle that comes bundled with your operating system and or your browser. And that's what allows server identity on the internet to work in a fairly seamless way. Client identity is sort of a mess, and that's largely because there is no common namespace for client identity. For server identity, we use DNS. Client identity, we just keep creating new PKIs, which all have their own namespaces, which are typically organization or application local. And then you really don't have a good standardized discovery mechanism for public keys. Um, and so it's, those challenges make PKI sort of hard to deploy. And then once you have it deployed, it's harder to really fully operationalize it. So, keeping that in the back of your mind, the problem space, let's look at what DANE does. DANE stands for DNS authentication of named entities. And this started years ago, RFCs 6698 and 7671. And then a whole host of other RFCs built on this for different use cases. But the idea is to use DNS to convey certificates or just raw public keys and a context for their usage. Originally, it was just imagined to serve as a way of, getting public keys into DNS for establishing server identity, either working in concert with or instead of web PKI. And it's current. There's a current effort at IETF to expand the use case to cover client and sender identity. And this is the DANCE working group, stands for DANE authentication for network clients everywhere. And so what this does is this binds client identity to the DNS namespace. And so, with that, by using DNS as that binding namespace, you can prevent identifier collisions. And what that, how that plays out in the real world is that every organization, since they manage their own part of the DNS, you don't have to worry about impersonation as long as you protect your DNS zone. And then DNS is also useful for public key lookup. So I mentioned a minute ago that there are no really good standardized ways to do public key lookup, except for some cases in like the email ecosystem. Everything for client identity is pretty much just proprietary APIs with a CA. And so by binding those identities to DNS, you also get a lookup mechanism that's already baked into the operating system. So the SDK is already there, and it's sort of ubiquitous. So what does life with DANE look like, once you implement it for client identity? Transport security. This is TLS client authentication. You can do identity management inside the application. I'm sorry. Let me back up for a second. The process of managing identities in an application that accepts DANE bound or DNS bound client identities is you really just have to add a DNS name to a role in the application. You don't have any shared secrets, no API keys. And so adding a name to an application role in the application, and then doing that verification, as the client tries to log in, it really takes a lot of complexity and a lot of sort of secret material that sometimes exists in a database. And you have to make sure that you're doing your, protecting your passwords right. If you move to an authentication mechanism like this, then you're not storing any passwords. You just have the location in DNS where you can look up the entity's public key, and the application footprint gets a lot simpler. And so another added benefit is, if you're examining how the application works, and you're trying to troubleshoot or track information flows, it becomes a lot easier to describe trust when you're describing trust between two different names in the same namespace. Compare this to if you're using, in a lot of IoT ecosystems, you see people using, just the hash of the public key to identify the device. And while that's can be fairly unique, the challenge with that is that it really doesn't tell you anything about the device. It's just a string, and to human eyes, it doesn't make a lot of sense. You have to pull in a lot of context in order to start looking at relationships between entities in an application. Um, Whereas if you're using DNS, you get a unique name that also reflects the name of the organization or domain that's responsible for managing that identity. And that could be even another organization and not your own. You would be able um, to allow client identities from anywhere in DNS. You just have to put their name in, and that grants access to the application. And so for a visual, because I realized that was sort of alphabet soup, you may have to zoom in on this slide. In fact, I'm certain you're going to have to zoom in on the slide because there's a lot of information on it. So what this is showing is the configuration of the application, right? So at the top, we have DNS, and this just represents kind of the tree under an example domain, example TLD. You have a device on the left, which has its own private key, and I've color-coded that with the certificate in DNS. The load balancer is configured to authenticate any certificate, which means you require in the TLS handshake for the client device to prove that it possesses a private key matching the public key in the certificate, but you don't have to prove a chain of trust. And so it authenticates that certificate and then passes the certificate into the Python application. The Python application is configured to allow any clients under another .example, and this just uses a wildcard match. So in the process of authenticating this, what you have is once the client authenticates using that first TLS authentication step, right? It proves that it has the private key matching the certificate that it's presenting in the handshake. The load balancer then passes the HTTP request as well as the certificate to the application behind it. The application behind it takes the client's name that's presented in the post data, and it uses that to next slide. And it uses that to grab the certificate from DNS. And so we have the name that the client identifies itself as. We have an authenticated certificate, and then the application behind it confirms that the certificate presented is the actual certificate for that named entity. And so this is how we're able to use DNS as that anchoring namespace and allow clients by DNS name, and without the trouble of having to onboard everything to the same PKI to get the benefit of public key authentication. And so, on the right of the diagram, it compares what comes in the certificate that comes in the header with a certificate that comes in from DNS. And if it matches, then it's considered authenticated. And before we go into the and end-to-end secure messaging use case, I'm going to roll the dice here again with screen sharing, and I'm going to try and show a demo of the actual, or a little bit more about a working application that employs this client identity method. So hold on just a second. And we can take some questions here too, if you have any.
Yeah, I don't see any questions just yet.
Okay. So the tab that I'm showing is a source code. I haven't released this yet because I'm not done picking at it. But the web application that I'm about to show you, this is super simple. It just has a couple of routes using Flask. And what it does is it grabs the the TLS client certificate that's forwarded in from Traffic. TRAEFIK is how that's spelled. That's the load balancer that I'm using just for terminating the server side of this TLS connection. And so what gets passed in, we make sure that, we do some basic checking that that we're getting the right host name for this to make sure that it funnels into the right sort of interaction. We grab the client certificate from the headers that come in, and from the form post, we get the DANE ID, which is just a DNS name. And then we have the message. And then we go through and perform DANE authentication of what's coming in. And we start with the DANE ID, which, remember, that's the DNS name, and the certificate that comes in with the header. And we just go through a brief validation process, and we use a library which is open source. It's called DANE Discovery, to actually authenticate this against DNS to make sure that what we're getting in DNS is what it should be. And the policy, this is actually, the policy is expressed in environment variables. It's just, I was looking for the smallest application footprint to demonstrate this, but it's, it'll take allowed domains as wildcards, and then you can allow specific hosts as entities. But this is something that, of course, in production, you would probably have in a database table. In the end, the point is, this is just a list of permitted DNS names, and then there's no sort of credential storage for that you have to do on the server side, because you're using DNS to do that public key lookup for all of your authentication requests. Now, to actually show what's going on in the application, I have this tab says authenticated messages. This is really unexciting. But this is pulling from a SQLite database that's sitting inside the application. And what I'm going to do is I'm going to use a curl request to populate that with a new message, and it just performs live authentication as this goes through. Again, with the sharing acrobatics, thanks for your patience. And so here we hit curl, and this device that's recognized in the response, we can use dig, which is a DNS troubleshooting tool that's available macOS, whatever you're using. And we look for a record type called TLSA, which is defined by the DANE standard. And then we use the name of the DNS name of the entity. And this right here is the certificate that's presented in DNS. Anybody in the world can look up that certificate by using that name. And so that's how we allow client identity to be as interoperable as server identity. And you can have clients, DNS bound identity can then participate in, multiple different applications, because it's an application independent identity. Anyway, we posted the message, we refresh the page, and so it goes. All right, now let's head back to the slides. So building on that concept of a DNS bound identity, What else? What else can we do with that? Um, you can have an entity that's operated or owned by one organization that uh, generates and signs a message that can be verified by any party receiving it, as long as that party has access to DNS. And since everybody on the internet pretty much does, that makes end-to-end signed messages really easy to do. The way you do that is you create a signed message, including the sender's DNS name, um, and then you protect all of that with signature using the private key that corresponds to the public key in the certificate in DNS. And then whoever the recipient is can use that name inside the message to go and retrieve that public key for authenticating the message. Independent of originating organization, as long as it's represented in DNS, anybody can authenticate it. Encryption for end-to-end encryption works similarly. So the sender can use DNS to grab the recipient's public key. So if you know the entity that's going to be unpacking this message, you can grab their public key from DNS, and then you use that public key to encrypt the message that's the signed message. And then this is how you protect information traveling over middleware, especially middleware that you don't own or control. And so you can get that end-to-end security so that even if your middleware is compromised, it's not an avenue for impersonation, and it's not as much of a breach issue if everything going across it is encrypted. And so, by way of illustration, this is what it looks like. We've got on the left, we have the blue device, generates a signed message, and before it places it on the broker, it grabs the recipient system's certificate from DNS. And on the next slide, the message that travels across the broker and is received by the service on the right-hand side. Once that message is unpacked, that service can use the sender's DNS name to go and retrieve the certificate from DNS to authenticate the message. And that's how you do end-to-end message security, using DNS as sort of that the public key lookup mechanism and namespace enforcement. So I think I came in right about time. We were going to shoot for 25 minutes, and I think I took about 23. So now I'm going to encourage you to have a look at our IETF working group. It's called Dance, and we actually meet at it'll be 4 a.m. San Francisco time that we're meeting on Friday. But feel free to if that's a little early for you to join, then feel free to join the mailing group. And if this is something that's useful to you, then we would love to get your feedback and kind of understand how this maps to problems that you're seeing in the real world. And there are a couple of Python libraries that you can pick up and play around with. There's one called DANE Discovery, which goes through the process of parsing the DANE record out of DNS and authenticating it if it's got DNSSEC attached to it, and there's another mechanism for if DNSSEC is not available. And then DANE JWE-JWS is another library which allows you to it sits on top of DANE Discovery and makes it really easy to do end-to-end secured messaging using JSON.